All right, section 3.8. We only have 2 sections left in the chapter. This is all about implicit differentiation and logarithmic differentiation. So this is kind of a nice break of all the heavy applications we've been doing and just look at a couple ways to differentiate more complicated functions. So in this, we want to do implicit derivatives as our first objective. Derivatives. And the second thing is we're going to look at logarithmic differentiation. Now this is going to be focused primarily on tower functions. W doesn't quite look like a W there. Okay. So implicitly defined functions, a function can be defined implicitly in terms of a variable, and what that means is that both your independent and dependent variables appear in the same equation. So if, let's say, y equals f of x, then an implicitly defined function will have y in the equation. So something like x plus y equals c. This is an implicit function. Now if we solve this explicitly for y, we have an explicit function. Y equals a function of x. But here what we're saying is we could really write this as x plus f of x equals c. Now we don't always write that because 1, it's faster to write it as y, and 2, a lot of times our implicit variables, our dependent variables, represent some sort of value or parameter in the real world. So when we are taking implicit derivatives, to take that derivative, we're going to use the chain rule. So we know y is f of x. And just for example, I'm going to use this function. So d dx of x plus y equals c means that we're really taking the derivative d dx of x plus f of x equals c. And so this is going to equal 1 plus f prime of x equals 0. Derivative constant is 0. Or what we'll oftentimes see is just 1 plus y prime equals 0. Now for a more complicated function, something like g of y, so let's say we do d dx on g of y, the same y though, so y is still a function of x, you could write that over here. Well, this is really a chain rule problem, and so we have d dx on g of f of x. And so we know that this is going to be g prime of f of x times f prime. And again, just like we can write this as 1 plus y prime, a lot of times you'll just see this as g prime of y times f prime of x. And f prime of x is just y prime. So this is a little weird to think about with these 2 specific examples, but we'll go ahead and work out this first couple. So differentiate the following using implicit differentiation and then find dy dx. So when it asks you to find dy dx, that means we need to solve explicitly for dy dx. We need to find y prime. So we have y cubed plus x squared y to the 5th minus x to the 4th equals negative 11. And so we're just going to differentiate this. So when we have this y cubed, we take the derivative like we normally would, 3y squared. Now because y is an implicit function of x, we know that because we're trying to find dy dx, we need that chain rule. So this is g prime of y, that's 3y squared, and now we need the y prime. And we literally just put y prime. Then here we have a product, so this is a product rule. So 2x y to the fifth plus 5x squared y to the fourth, and then we need that y prime. So we times by y prime, and then minus 4x cubed equals negative 11, or equals the derivative of negative 11, which is 0. So now, when you take your implicit derivative, you'll have some terms with x's and y's and some terms with y primes. So we're going to factor the y primes out of what we can. 3y squared plus 5x squared y to the fourth plus 2xy to the fifth minus 4x cubed equals 0. So when you're finding dy dx with these implicit derivatives, you always have to factor that out, and then you're just solving for y prime, is essentially what the last of the problem is. So we are adding and subtracting these terms, and then going to divide by this. So I'm going to do it all in one step. So we add 4x cubed and subtract 2xy to the fifth, and then divide by everything here, which is 3y squared plus 5x squared y to the fourth. And so that is our derivative, y prime, or dy dx. Remember, y prime equals dy dx, just another notation. So these problems will always have you end up solving for y prime. And then if you can simplify, maybe you should. If you're going to be taking another derivative, notice this is another implicit function. It's going to be easier to do it once you've solved for y prime, because then you'll have y double prime right here, and you won't have any y primes here. So this function is no longer implicit. It's implicit in y, but it's not implicit in y prime. So if you're going to take a derivative, you'll have y double prime equals some stuff. Now it'll have y primes in here, but that's why we solve for y prime, is that then our derivative will not have y double primes on the other side, just like this had y primes everywhere. Once you solve, you eliminate that issue. Okay, so let's move on to the next one here. We have x equals the square root of 200 minus p cubed, and we were asked to find dp dx. So that means p is the independent variable. So p takes the place of y like it did here. So when we go to take our derivative, we do it like normal. Derivative of x is 1. This is the 1/2 power, so bring the power down. Leave the inner alone. 200 minus p cubed. 1/2 minus 1 is negative 1/2. And then times the derivative of the inner. That'd be negative 3p squared. That's the g prime of y. And now we need the y prime. And that gets tacked on at the end here, y prime. And now it's just about solving for, oh, I put y prime, p prime in this case. Now it's just about solving for p prime. So I'm going to write this as 1 equals negative 3p squared p prime over 2 times 200 minus p cubed to the positive 1/2. So just switching this to the bottom. And then solving for p prime, we're going to multiply by the denominator and divide by what's left in the numerator. So we're going to end up with p prime equals 2 times 200 minus p cubed to the 1/2 over 3p squared. And that's our derivative of that function. So we turn the page here. Got 2 for you to practice. So I would recommend you pause and try these on your own. And I'm going to walk through them here. One quick note. This says dw. I don't know why it's w. It must have been w in a previous version. This should be dp dy, not dw. Just in case you jump into that. Dy dx is fine on this one. So pause the video, try this out. Great. Let's check your answers. So our derivative, we need a product rule. So this is 2y, y prime, times x, plus 1 times y squared. Then another product rule here. This is 6x squared times y cubed, plus 6x cubed y squared times y prime. And then this is going to equal y prime plus 0. So now I'm going to move this y prime over and factor it out. And so we're going to have 2yx from this term. We're going to have the plus 6x cubed y squared from this term. And if I subtract this over, then that's going to give us a minus 1 here. And then the other terms I'm going to move, so this y squared I'm going to subtract over, negative y squared. This 6x squared y cubed I'm going to subtract over, negative 6x squared y cubed. And now we just divide. And we have y prime equals negative y squared minus 6x squared y cubed all over 2yx plus 6x cubed y squared minus 1. And that's our derivative. Now what you may have noticed in the last two examples in this practice problem is your implicit derivatives are ugly when they're done. They are very, very nasty looking. But if you have a point, let's say x and y, you just plop in the x value and the y value where you have it. Okay, so this next one here, we're doing dp dy, so y is the dependent variable, or the independent variable, it's acting like x, and p is acting like y. So our derivative then will be 1 equals, this is 2 times 1 plus p squared to the 1/3. So this will be 2/3, leave the inner alone, 1 plus p squared. 1/3 minus 1 is negative 2/3. And then the derivative of the inner is 2p p prime. And then we need to solve for p prime. So I'm going to rewrite this as 4p p prime over 3 times 1 plus p squared to the positive 2/3. So that's just moving this term down to the bottom and then multiplying 2 times 2 to get the 4. And then p prime is going to be 3 times 1 plus p squared to the 2/3 all over 4p. That's our derivative. And again, if you had a point, p comma y, you would just plug that in. Or y comma p in this case. You just plug in your p's. This doesn't have any y's, as it turns out, so good news for us. That's our derivative. So the homework has some problems, obviously, for you to work this out. And the worksheet does as well. So the next thing is logarithmic differentiation. And like I said, our primary function that we're going to be using logarithmic differentiation on is tower functions. So a tower function is a function that is f of x to the power of another function g of x. So the classic example is like x to the x. And in fact, we're going to take the derivative of that in a second. But logarithmic differentiation allows us to take the derivative of this. So if we have f of x equals g of x to the h of x, logarithmic differentiation really means we're just taking a log of both sides, and the log we always pick is ln. So ln of f of x equals ln of g of x to the h of x. And we know that our logarithm properties allow us to bring the h of x down. So this means that L of f of x equals h of x times ln of g of x. And now we can take the derivative using a product rule, using chain rule on the logarithm and the logarithm, but it allows us to do it. However, this is not the only use of logarithmic differentiation. It's certainly the most beneficial. But let's say we have this function in this example. This does not require logarithmic differentiation. You can do it with a product rule, a bunch of power rules. But we can make it a little bit easier on ourselves if we use logarithmic differentiation. So if we take the ln of both sides, we have ln y equals ln of x to the fourth plus 3x plus 1 cubed times, I'm going to write this as the 1/2 power, 1 minus 3x to the fifth to the 1/2 in that logarithm. So now because we have a product, we can split this into two logarithms. ln y equals ln of x to the fourth plus 3x plus 1 cubed, and then plus ln of 1 minus 3x to the fifth to the 1/2. And we continue to use our logarithms to bring these powers down. So ln y equals 3 ln x to the fourth plus 3x plus 1 plus 1/2 ln of 1 minus 3x to the fifth. So we still have some chain rules, but no more product rule. And these are a little bit simpler to do than these chain rules were. So now we just use our definition of our derivative of ln. So that's going to be f prime over f, or y prime over y, equals 3. The derivative of the inner is 4x cubed plus 3 over itself, x to the fourth plus 3x plus 1, plus the derivative of the inner is negative 15 x to the fourth over 2 times 1 minus 3x to the fifth. And the last step is to solve for y prime, because we always solve for y prime. So y prime is going to equal, put some big brackets here, 12x cubed plus 9, distributing this 3, over x to the fourth plus 3x plus 1, minus 15x to the fourth over 2 minus 6x to the fifth, distributing the 2, and then times the original y, which is this wonderful thing. And I don't have enough space, so I'm going to write it below. X to the fourth plus 3x minus 1 cubed times the square root of 1 minus 3x to the fifth. So this times is getting linked here. So again, just like with the implicit derivatives, logarithmic differentiation always looks gross at the end. Maybe it's not the fastest or the cleanest, but it does allow us to take derivatives a little bit simpler using logarithms. This was an extreme case with these big functions in here. So let's try it on some tower functions now. So here's the classic function, y equals x to the x. And this is the classic tower. So taking the natural log of both sides, ln of y equals ln of x to the x. We can rewrite this as ln y equals x ln x. Now we take the derivative of both sides. This is going to be y prime over y equals, derivative of the first is 1 times the second is ln x plus x times the derivative of the second is 1 over x. So this is y prime equals ln x plus 1 times y, moving that over, which is x to the x, because we always solve for y prime. And you don't need to simplify any more than this. So that's for tower functions. The last example was for just in general, you can use logarithmic differentiation anytime you have products and chains and stuff like that. Sometimes it makes it life easier, sometimes it doesn't. So these next two, again, practice problems here. I recommend you try them. Actually, I think the next three are all practice. But try these out using logarithmic differentiation. Just take the log of both sides and then solve it for y prime. So this one's ln of y equals ln of 3x squared minus 12x to the 4x plus 1. So at this point, you should be pausing the video, trying this out. I'll walk through it now. So this is ln of y equals 4x plus 1 times the ln of 3x squared minus 12x. So this is going to be a product rule. Y prime over y equals 4 ln 3x squared minus 12x plus 4x plus 1 times derivative is 6x minus 12 f prime over f, so 3x squared minus 12x. And then the last thing to do is to solve for y prime. So this is 3x squared, oops, it's not plus, it's minus 12x to the 4x plus 1, all times this, 4 ln 3x squared minus 12x plus 4x plus 1 times our fraction 6x minus 12 over 3x squared minus 12x, and our brackets. And that's the derivative there. Again, you could simplify this, but we don't need to. It just opens us up to more errors. But that would be our derivative. Now there's no way to take the derivative of this function of tower functions in general without logarithmic differentiation. So if you're wondering, do I have to do this? The answer is yes, you do. Okay, so on the next one, hopefully you've tried it. If you haven't, pause and try it now. We have ln y equals ln of 19x squared plus 4 square roots of x to the e to the 4x. So this is ln y equals e to the 4x times ln of 19x squared plus 4x. I'm going to write it as the 1/2 power now. Take our derivative of both sides. Y prime over y. Derivative of the first, 4e to the 4x times ln of 19x squared plus 4x to the 1/2 plus e to the 4x times the derivative of the second, which is going to be a fraction. On the bottom goes 19x squared plus 4x to the 1/2. On the top goes 38x, and then plus 2x to the negative 1/2. And the last step is to solve for y prime by moving the y back over. So this is 19x squared plus 4x to the 1/2 to the 4x plus 1 times what we have written here, 4e to the 4x ln of 19x squared plus 4x to the 1/2 plus e to the 4x times the fraction 38x plus 2x to the negative 1/2 all over 19x squared plus 4x to the 1/2. And then we close our bracket. And that is our derivative. Again, very ugly, very gross looking, but we don't need to simplify further than this. Again, these are some difficult ones. If you can handle these, the problems that you see in the homework on the worksheets and the quizzes, they'll be a lot easier. These are to show you how gross it can look compared to how nice it could be. All right, so there's one more practice. And we actually saw this. This is a logistic curve. This is a logistic model. And we did this with the quotient rule when we did this back in 2.4, 2.5. I can't remember exactly. Now I want you to try it using logarithmic differentiation. So take ln of both sides. ln equals ln of L over 1 plus CE to the negative RT. And you should be pausing here, using your properties of logarithms, and trying to take the derivative. Okay, great. So our properties of logarithms say that we can split the division to ln of L minus ln of 1 plus CE to the negative RT. And now we take the derivative. Y prime over y equals 0 because L is a constant. 0 minus, it's going to be a fraction. 1 plus CE to the negative RT goes on the bottom. And this is going to be the derivative of the inner. So it's going to be negative CRE to the negative RT. And so y prime over y, simplifying a little bit here to make our lives easier, CRE to the negative RT over 1 plus CE to the negative RT. And the last step is to multiply by y, move it back over. Y prime equals L over 1 plus CE to the negative RT times CRE to the negative RT over 1 plus CE to the negative RT. Now this is fine, but remember we've done derivatives like this with the quotient rule. So if we do simplify, notice the denominators are the same. So this just becomes LCE to the negative RT over 1 plus CE to the negative RT quantity squared. And if we're looking at our original function, quotient rule says low d high minus high d low. Well, minus high d low, we'd have the minus in here that's plugged in. So minus high, this would be negative L, times the derivative of the low, which is this, which has the minus, which is why it turns to plus, over low squared, over the denominator squared, which is exactly what we have. So the purpose of this was not necessarily to show you that logarithmic differentiation gets you the fastest answer. So as you see more examples and more problems, you'll realize when do you want to use logarithmic differentiation, or when do you want to just stick to the classic rules, quotient rule, product rule, chain rule. If you like logarithmic differentiation, you can do it anytime you have a product, a quotient, a chain. Especially you can only use logarithmic when you have a tower. Or you can just stick with chain or quotient rule in this case, or chain rule, or product rule. You'll get the same answer. It just might look different because of simplification. Right? You may not guess that this is the same until you simplify it. But that's the end of 3.8.